Let me announce one of the key presentation of today in our first session, which specifically dedicated to coherent acoustic phonons, which is actually, I would say, on the background of the whole conference, because we are interested in that a lot from the point of view of practical technologies, applications. From one side, there isn't theoretical results from other side, theoretical and experimental results from other side, and from the third side, we have a great demonstration how coherent acoustic phonons can be used in technologies and applications. Again, I would mention that we have the whole industry right now of building electro-optical devices based on coherent acoustic phonons or the strain generated in indirect semiconductors in order to build it's a huge business in Silicon Valley, in China. They have some clusters like MIT spin-offs. So this is a hot topic right now. So it's very interesting to have this kind of very well vertically integrated field, where the one side is the fundamental research, another side is the practical applications, which is on the market right now. So you can buy this germanium light emitting diodes based on the silicon on the market and to use it. So let me introduce the Professor Andrey Akimov from Nottingham University from the University of Nottingham in the United Kingdom. He's one of the pioneer of the coherent acoustic, not coherent, but non-coherent optical phonons and acoustic phonons, both phononics, I would say, from from the last century, did a lot of work on that in his matter, and he brought this great experience to the United Kingdom and leading a lot of efforts on that. So Professor Akimov will present to us emission and absorption of coherent acoustic phonons during ultrafast phase transition. Professor, please.
So hello, ladies and gentlemen, and thank you very much, Mike, for introduction and for describing this. From one hand, it's quite traditional topic, and from another hand, it's quite a lot of perspectives there. So this work, which I will tell about phonons and about phase transition, is collaborative work. The experiments were done in Yoff Institute in the group of Alexander Kalashnikov, who's present at this conference, and then the samples were prepared. The samples, it is vanadium dioxide, and about vanadium dioxide there were a couple of talks yesterday, and it is very popular material when somebody studies ultra-fast phase transition. These guys prepared the samples in the University of Puerto Rico, and we with Tony Kent were involved in this work quite actively, and we are from the University of Nottingham. So if we look, I don't know what's how to switch. Oh yes, yeah. Sorry. So if we look at these topics, ultra-fast phase transitions and coherent phonons, these at a glance, they're very different. From historical point of view, they started at the same time, approximately in 80th, long ago, and it was development was related to the rapid development of the ultra-fast lasers. So actually in ultra-fast phase transitions, which are induced optically by optical pulses from the lasers, there are a lot of types of these phase transitions. The materials where this phase transition takes place they are quite well known from equilibrium studies. So all these materials, almost all, they have phase transition in equilibrium when we change temperature, but then exciting it with a short laser pulse, it induces phase transition. And it appears that in many materials, they're going in on a very, very short femtosecond time scale. And there are still many fundamental questions left. And what's concerning mainly to the microscopic mechanisms of these photo-induced phase transitions. And this concerns actually all phase transition, insulator metal, actually, what is vanadium dioxide is, and structural phase transition, which accompanies many other phase transitions. The insulator metal transition is accompanied with a structural phase transition in vanadium dioxide. And of course, phase transitions in ferromagnetism, ferroelectricity, they're all of interest. If we now turn to coherent phonons, as I said at a glance, it is not very related to phase transitions because currently the main task is mostly technical task is to go to as high frequencies as possible, to as high amplitude of elastic waves, acoustic waves of very high frequency, to high amplitude as high as possible. And then if it is realized, and partly it is realized to some extent, then imaging of nanometer objects could be possible. Then also ultra-fast control of electronic and optical devices become possible, and ultra-fast control of magnetization by coherent phonons, similar as people do with light, say could be possible with phonons. And I would say there are a lot of also achievements in this fields, and actually what I show on this slide concerning imaging, ultra-fast control, and magnetization, they're actually realized and published in several papers. But what is common between ultra-fast phase transitions and coherent phonons? I would say that, and this is about my talk, is stress, and stress is also related to strain. So even in equilibrium, if we consider phase transition in equilibrium, say for vanadium dioxide, the temperature of phase transition, which is slightly above room temperature, it depends on the strain. And so then another point is that when phase transition takes place, whether it is equilibrium or photo-induced phase transition, then the lattice changes. For us will be important that the lattice constant change. First of all, the symmetry of the cell changes, but maybe this concerns mostly optical phonons, but concerning acoustical phonons, it is important that the size of the cell changes, and then the lattice constant changes, and this results in the strain, of course. And relation of strain and stress to elastic waves is obvious, because actually phonons, which is in classical presentation, is a strain wave, and actually the strain is the main feature of these waves. In optics, it's electromagnetic field. Here for phonons, it is strain. So basing on this a bit extended motivation, I would say, not motivation, introduction, I would just go to outline. So I will tell about, in introduction, about generation of coherent phonons, just a very simple example how to generate the wave packet of coherent acoustic phonons. And then I turn to generation of picosecond strain pulses, and strain pulse is actually the wave packet of coherent acoustic phonons. And I will tell about the experiments where strain pulses are generated and injected into the crystal as a result of a photo-induced phase transition. Then the last part will be the effect of coherent phonons on photo-induced phase transition in vanadium dioxide. So at first, how we may generate acoustic phonons. This is a very simple example. It is actually the generating of the strain pulses. So we have a crystalline material. It actually doesn't matter. It matters that it is solid. It may be amorphous material. And then there is a metal film, thin metal film, typical 100 nanometers or smaller. And then we excite it with the laser pulse. It hits the film expands, and then it happens quite quickly, and then this strange pulse is injected into the crystal. This is all known from 80th. You see, 86 was this famous work by Thomson and Morris, which they just generated strange pulses in such a way. Let us look once more how it's going. So the pulse is hitting the film, and it is like a kick of a hammer, and then the strange pulse is injected there. So in a simple way, in this simplest, I would say, way, this strange pulse is bipolar. So this is compression part is the first, and then it goes in tensile part, and it is propagating with sound velocity. In the most of cases, it is longitudinal sound velocity because it is only compressed wave. In principle, it's possible to generate shear waves. I shall not tell about, but people do this. Then the typical size of this is tens of nanometers. The duration is about 5 picosecond. And if we take a Fourier transform of such pulse, then we shall get the spectrum of coherent phonons, and the maximum will be, it depends on, but between 50 and 100 gigahertz, depending on the thickness of the film and some other properties of this metallic film. And this is what I tell is the simplest mechanism, is thermoelastic mechanism, so-called, that the film is expanded, so the strain is generated due to heating. And the amplitudes may be quite high, about 1%, but it requires very high temperatures. Say for aluminium, if we take aluminium film, it requires to heat up on 400 K for aluminium, and say for chromium, it's even more. So people go usually up to, if they want high amplitude, it's just eventually they destroy the film, and there is a hole here, and nothing works anymore. But the idea with strain, with the phase transition, maybe it is possible to generate without heating, and then we have a strain pulse, but no heating of this material if we just do something with strain, with the phase transition. And this is the idea which I'm coming to. And this will be generation of these picosecond strain pulses during ultrafast photo-induced phase transition. But maybe I would add one thing, is that this is, as I said, the simplest way, but there are methods where we may generate quite high amplitude of coherent monochromatic phonons. There are special structures used, special materials, but it is all possible nowadays. But this is, I will, in my talk, the simplest example is most, I would say, relevant. So, vanadium dioxide, very well-known material, and at room temperature, it is in monoclinic phase, and it is insulator. If we, just in equilibrium temperature, it is known that around 60 Celsius, it is just transferred to metallic phase, but it is also known from the first works by Cavalieri that if we excite the system with femtosecond pulse, and it just transforms to metal, it will be vanadium dioxide or metal, and the structure will be tetragonal. So the structure for us, it's to some extent, it is important that it was insulated, becomes metal, but the main thing, it's important that it was monoclinic and becomes tetragonal or rutile. So the important thing is that there is no lattice heating during phase transition, because it is first order phase transition. Then the crystalline structure changes in a time of about 100 femtosecond. It is studied all with X-ray and electron diffraction. This is all known. The lattice constant changes on about 1%, but with the lattice constant, it doesn't change so fast. It cannot actually change so fast because it is all related with the size, with the geometry of the system, and it is related to the sound velocity in the material. But anyway, at first, how strain it, for us, it's important the strain, but at first, of course, stress is generated. So transition takes place very, very fast, in less than 100 femtosecond, and then the stress appears in the system, and then the stress starts to work. For elementary cell, it works very fast. For lattice constant, it works longer, but we shall see how it is working in practice. So this is the experiment. What we do, we have sapphire substrate, and then there is this VO2 film, homogeneous film. It is made especially on this orientation of sapphire. Then we have a pump pulse, and we may just excite, changing the intensity of this pulse, we may control the amount of material which possesses a phase transition. And then we see that we shall see that the strain pulse in the same way, to some extent, in a similar way as I showed with aluminum, is ejected. It is propagating through the substrate, and we detect it with the chromium film. We're using photoelastic effect, so measuring the reflectivity with time resolution. The important thing which we use here is nonlinear properties of sapphire, which are well known, where all parameters are known. And if the strain pulse has quite high amplitude, it shrinks. It expands in space and in time. It stretches, and this stretching is somehow it's well-known dependence on the strain pulse amplitude, and then we may model this stretching, and there are some examples. So what pulse is injected, and then what is happening in some time when the strain pulse is approaching this chromium film, and then eventually what we measure due to the fact that pulse is reflected from the surface, then we measure these two sharp pulses, and then this time is related to how the pulse was stretched. And then we may calibrate, this time, and from measuring this time, which we may do quite precisely, we know the strain amplitude, which is injected into the crystal. So we may say what strain amplitude is injected into the vanadium, from vanadium dioxide to sapphire. Now, these are the examples when we do these experiments at room temperature when it is insulated, and then at elevated temperature when it is metal. So this is just the examples that we show that we may measure this time between first peak and the second peak quite precisely. Then if we know the time, then we know the strain amplitude. And so we plot this strain as a function of absorbed energy in vanadium dioxide film. And what we see, the most interesting things are happening when it is initially in the insulating phase. So at first we see some linear increase, and then we come to the threshold of the phase transition. So there is an energy when phase transition starts, and then the strain pulse amplitude goes rapidly. It increases rapidly, and then when we go to the power which corresponds to the saturation, so all material in the film, excited material is transformed to another phase. Then again, we have some linear dependence. If we just start these experiments in metallic phase, nothing nonlinear is happening. This is just this linear curve. And first of all, we attribute this nonlinearity. Nonlinearity in this region, which is observed only there, we attribute to the phase transition, and then actually what can we get from there more quantitatively. So we start to analyze, and then all parameters are known. So like specific heat, sound velocity, all these are known, and then we say that okay, while we are before the threshold, it is heating, and then there is a thermal expansion, and then we just get this black dashed curve. Then in this region, it is a bit more complicated because we need to take because the energy actually is absorbed, but all energy doesn't go to heating. It goes to phase transition. So there is actually no heating anymore, and then again the heating starts. So this dashed curve gives us this thermoelastic mechanism, which gives the strain much less, almost 1 order of magnitude less than what we measure. Then we need to add deformation potential. Deformation potential is coming from electrons from carriers which we excite optically. It is known that they generate stress. If stress is generated, then strain may be generated, and then we just we don't know. This parameter is not very clear with this parameter. We don't know the deformation potential. But we assume that it is there in the insulating phase. We just put it that it should be, there is nothing else except thermoelastic and deformation potential, so we put it there, and then we continue this curve, and again here there is no strong nonlinearity. And then what is coming else, it is just due to the phase transition, due to the changing of the lattice, due to the rapid changing of the lattice, so that the strain pulse is injected into sapphire substance. And you see the fraction of this is quite big. It is about 0.4% of the strain. And actually the strain amplitude may be very high. It is about 1.3%. No, actually in metallic phase, it is also, this material is very good. But in metallic phase, we heat the sample, and here we don't heat the sample. We heat it, but this heating is quite small, and this we may compare on this graph. So actually, what energy is absorbed, and what is laser-induced temperature, and we see that if the material is insulating phase, we get this high amplitude strain only for the temperature rising of 28 degrees. So it's comparable, say, for aluminum, it is 280 K, and here it is only, so it is actually the order of magnitude less heating with the same strain amplitude. So this is the first part where we generate these strain pulses. Now we're going to the second part. Second part is actually, to some extent, it is opposite. So it may be considered as an absorption of coherent phonons, and again we shall deal with the picosecond strain pulse. So the scheme of experiment is a bit different from another. It's a way around, I would say. So we have a vanadium film, which is not actually the film. There's a VO2 nanohelics. We call them nanohelics. Actually, these are vanadium dioxide nanoparticles, which are standing separately on the sapphire substrate, and then we generate quite high amplitude strain pulse, which is generated in aluminum transducer. It is in the same way how I showed you in the first slides, and then the strain pulse is injected. It is propagating through the sample, and then it affects vanadium dioxide film, where the phase transition is excited by the this red line, which demonstrates the pulse excitation, pump excitation of the phase transition, and we may control the amount of material which possessed the phase transition by measuring the reflectivity of this probe pulse, and then I shall show the examples how it works. Say this is without strain pulses, this temporal evolution of reflectivity. So we excite here we excite here VO2 nanoparticles, and then we see the changes of reflectivity. Actually, such kind of experiments have been done in many works, and this we actually, for us, it is just characterizing the material, and we see here that above some threshold, the phase transition starts. The amount of material which possesses phase transition, this goes up, and then there is at some point there is saturation, and then which means that all material is transformed to another phase, to rutile metallic phase in vanadium dioxide. The important thing will be that phase transition, and it is known, is happening at very short times. It is less than 500 femtoseconds, so both insulated metallic and structural phase transition. And then there is some stage which is called metastable state, and what is happening in this metastable state, it is not really very clear nowadays because it depends on a lot of parameters. But the main thing is that phase transition happens at a very short time, and then what happens next, it maybe people not, I wouldn't say not interested, but there are still questions about this. So the main thing is that measuring the reflectivity, we obtain the fraction of the material which have possessed the phase transition from insulating to metallic, from monoclinic to rutile phase. So then, as I said, we see how phase transition takes place during the strain pulse, when coherent phonons are coming. This is the time evolution of strain, which we measured exactly in vanadium dioxide film. I shall not go in details. It is a bit maybe more boring how to measure all this, but the main thing is that there are parts which are labeled as one as compression. The strain sign is negative, and this is compression. This is shown on this axis that it's negative. Then points 2, this is regions 2 is actually tensile parts. And then there are some points where strain is almost 0. And now what we do in the experiments, we excite the phase transition when there is compressive strain, and then we see what is happening with the phase transition, how it is excited. Maybe phase transition will be accelerated or it will be retarded. So we want to know what will happen if we excite the phase transition at this moment. And then we excite it when there is tensile part. We also are interested what will happen with the phase transition when we excite it in this time. And then we excite it, say here, it is, one may think, oh, but nothing should happen. Yeah, but it is not very clear because maybe nothing will happen. But there is, after this, the system, as I said, in metastable state, and there's still strain, compression, and tensile coming, and what will happen then? So I would say that such kind of experiments, time result, it is not possible to do anything in the equilibrium, because we may put strain in equilibrium, tensile or compressive, but to say to change it in the same place from tensile to compressive, and to see what is happening on metastable state, it is not possible in equilibrium conditions. And in this with this method, it is, with this technique, it is possible. So I will show the results first. What is happening with tension when we excite the strain, when we excite the phase transition at the moment when it is tensile part of the strain pulse. So the upper curve is just the scheme, and here we have the experiment. Actually, what is happening? We observe that the amount of material, relatively to the case of zero strain, the amount of material which possess phase transition increases. So we have this increase, and then if we monitor this in time, we see that this increase decays in about 1 nanosecond. Actually, the time much smaller than the lifetime of the metastable state. So this we have here. We have increase. I would say, and you will see the graph what we measured in compression. But it is interesting that if we excite it here before the strain pulse, and then the system goes to some metastable state, it goes very quickly, as I said, in much less than 1 picosecond. So we excite here, and then in less than 1 picosecond, we measure what is happening, and actually we see this happening nothing. We see that there is no changes in the amount of material what is going from one phase to another. This is the summary of this phase of these results. So in tension we have increase decaying with about 1 nanosecond. In compression we have decrease. Here we have increase, decrease, and this happens only when we have a pump fluence between the threshold and saturation. If we have there is actually no effect if we are below the phase transition threshold, or if we transfer all material from one phase to another, then the strain doesn't have any effect. So the important thing also is, I would say the most interesting is that only the moment of the optical pulse impact, the magnitude and size of strain pulse, has the effect on phase transition, and on other time it doesn't affect phase transition. And this brings us to such a model explanation, qualitative explanation. I would say that this is not very developed in the theory now, but some models use this two well potential to describe the phase transition. So there is this the energy, the full energy of the system is blue curve is the ground state, and you see the lattice is distorted relatively to rutile phase. And then the red curve is the excited state. It is when electrons and holes are excited, the system is in the excited state, and then we excite the laser with the laser. The system goes to this stage, and then very, very quickly it just relaxes and it gets to the rutile stage. And eventually, this is how phase transition goes in this model. Now let us put strain. Let us put compressive strain. So you remember compressive strain retards phase transition. So there are theories which show that in this case, this excited state goes a bit down, and then we excite the system. It goes, but it is low in energy, and then it cannot relax. It cannot go to this point. It stables there, and the system is stuck in the metastable state, and it is stuck in the metastable state relatively to some equilibrium for about 1 nanosecond. You see, let us consider this situation where the strain comes later. So we excite the system. This red curve is like without strain, then it relaxes, it stays in this point, and after that, this strain doesn't do anything. It will modulate, of course, this red curve, but this energy will not be enough to go for the system from this from this minimum to this minimum. It should go above or tunnel, and these times are much longer than this strain affects the system. So this is the story. I think I didn't take a lot of time for this, and these are the main conclusions that we generate the strain pulse, and this strain pulse is high amplitude and the system is not heated. It is not, the temperature is not risen at these experiments, and then the coherent phonons may accelerate or retard ultrafast phase transition. And phonons have an impact only during optical excitation of the phase transition. And thank you very much for attention.
Thank you very much, Professor Akimov. Questions, please. Barbell, please.
It's Matthias has his raised hand. Go ahead, Matthias.
I see. Okay.
Yes.
Okay.
Hi, Matthias. Hi.
Andrey, very nice. I like the calibration of the strain by the nonlinear propagation. However, I'm not quite sure. It seems like you have the assumption that if you put a laser pulse, the phase transition eats up all the energy, and you are not putting more energy into the phonons if you increase the fluence. I think this cannot be quite true. So have you checked how the result changes if you continuously add energy to the phonons if you increase fluence? I think it won't change much, but I think this assumption shouldn't be accurate. Or can you argue why the phase transition eats up all the energy and there's no energy in the phonons?
Actually, it is found in some earlier works that the energy which is needed for phase transition, for optically photon-induced phase transition, is equal to the latent heat, which is measured from in equilibrium. This is another question why it is the same, because in one case it is equilibrium, and in another case it's electrons and holes. But this is another question. But you are asking that why we actually don't, why we say that all energy is going to the phase transition and not to phonons, yeah? And this is, I would say, because in several works it is shown that there is, during this, in this region of excitations, and actually this is equal to the latent heat. Of course, I would say a fraction could be going, but still, whatever we do, even if all energy goes to phonons, there would be no nonlinearity.
Sure. Yeah, I assume that the nonlinearity stays, but I'm pretty sure that you cannot switch off the electron-phonon coupling by the phase transition, so there should still be energy going into the phonon. But okay, I'm happy with your results. I will study your paper. I didn't know it. Thank you.
Okay, welcome.
Barbell, please, your question.
I don't have a question. I just clapped to acknowledge the nice talk.
Oh, I'm sorry. Well, I'm sorry. Okay, the more questions, please. Okay.
Keith wants to ask. Keith Nelson wants to ask something.
Keith.
Yeah, can you hear me? Can you hear me?
Yes.
Yes.
Yeah. So of course there are lots of materials that have significant, lattice parameter change with phase transition. So it both for generating strain, but in particular for the second part of using that to influence the phase transition, it would sure seem like there's a huge range of materials for which this should have maybe a bigger effect than what you see. I'm even a little bit surprised that the effect in VO2 is not larger than this.
Maybe I agree. We are searching. It is a point of time, and people who are involved. Yeah, I agree that if we and your work on terahertz, on the influence of terahertz pulses on the phase transition is and to some extent they are related.
Of course, sure. But one thing, I'm not sure if this would work at all, but a fairly simple material would be zirconia. So you might just take a look. It could be useless. I am.
Yeah.
But it has about a 1% strain upon phase transition, and there is some study that would at least make that simple material seem hopeful to me for strain generation, but maybe more for control.
Yes, yeah. I agree. And I hope very much that we shall, especially with Sasha Kalashnikov, we shall be able to do something with magnetic material, with ferromagnetic phase transitions. Yes, you're right. You're absolutely right.
Great.
So, Matthias, please.
Yeah, if I may again, because we have time, this multiple wiggling of the strain, is it because the strain wave gets reflected within the VO2 at the surface? Or why do you have multiple bipolar strain pulses?
But first of all, it has multiple due to aluminum. This is the main thing. Aluminum on sapphire, they are not very well meshed. Say sometimes we use chromium, which are much better, and then there are no. But this wiggling is due to to reflections in aluminum on sapphire, and actually quite thick aluminum film. We use more than 140, which is just actually it's.
Okay, so Keith Matthews, who else?
No, I would have a question.
Okay, you?
Yeah, I'm Bärbel. So sorry, I came late, but just from your answer now, is this wiggling frequency dependent on the thickness of your material?
On the thickness, in this case, on the thickness of transducer where the pulse is injected, it's aluminum. It is not related to the phase, to the material where phase transition is. But in principle, in some experiments, it depends on the thickness. It may be due to the multiple reflections in the system, but there may be even resonances. Yeah. Everything depends on the acoustic mismatch between the substrate and the film, and there may be breathing modes. There may be some kind of a lot of.
So, I just thought if one can steer the frequency of this wiggling, maybe it can be useful for something.
So sometimes in this particular material, this frequency is quite low, so it doesn't attract a lot of interest. But say two-dimensional materials, yeah, with phase transition or without phase transition, doesn't matter. The frequency goes up to 1 terahertz, and the quality factor is quite high. Then there are superlattices where there are systems where these wiggles maybe for a long time and with very high frequency. This is, of course, interesting for phononics.
Yeah, thank you.
Thank you. Professor Akimov, I have a few questions, if I have time to ask these questions. The number one, you mentioned the different phase transitions and different phenomena arising from the strain related. The two more is pretty much old, but to some point may be interesting. It's a piezoelectricity and electrostrictions. I'm talking about in both ways, there's piezoresistivity and a piezo charge generation and electrostriction as well. If you can couple words on that relative to what you observed, what you did.
This is very interesting. I would say we have in the University of Nottingham, we have access to ferroelectric materials, to 2D ferroelectric materials. This is a very hot topic and it is very new. We have it in mind, but then time and people who study this, but yeah, you're absolutely right. This may be very, very interesting thing.
Okay. There is a time frame for thermal expansion. What you can say about that?
First of all, when we excite optically, you mean perhaps, yes?
Yes, sure.
So first of all, there should be stress generated. So energy from electrons should go to phonons, non-coherent phonons, not phonons which I was telling about, non-coherent phonons which is heat. Yesterday there were several talks which were describing this, and this goes quite fast. there are two temperature models, so-called, which describes all this, but eventually this goes in less than 1 picosecond. It depends on the material. In semiconductors, it may be longer. In metals, it will be faster. And then stress to strain. Yes, and it is in metals. In semiconductors, there is another mechanism. There is a deformation potential. When we excite electrons to excited state, there is another parameters of electron phonon coupling, and there is deformation potential, which gives you stress. So you create stress almost immediately in less than 1 picosecond. In the phase transition, it is also less than 1 picosecond. It is very fast, generating stress. And then stress goes to strain. This depends on the thickness. If material is very small, then it will go fast. It's just you take the size of material, the smallest size, I would say, and divide it by sound velocity, and then you will get this time. And this actually gives you the typical frequency of coherent phonon. What is emitted? It may be broad spectrum, it may be narrow spectrum, but it gives you eventually what you have. And say for 100 nanometer film, it will be about 50 picosecond, I think, something like this. And this gives you 20 gigahertz. So, okay, it may be 20 picosecond, 5 picosecond, maybe. It depends on the thickness of the film.
Okay, thank you. And the last, I'm sorry for that, so many questions. Metastable phase, what you mentioned. Did you have some expectation what it could last?
You
mentioned the metastable phase induced by ultrashort pulse, metastable phase. How you said you didn't go into that, but you guess how long it may last?
Metastable.
Yes.
Oh yeah. It is. So without strain, without coherent phonons, these last for microsecond, I think.
Yes.
But it depends what to call metastable state. It is so. Of course, it is non-equilibrium from the point even if it is equilibrium, you may describe it by temperature, but say the substrate may be another temperature. So from this point, it is non-equilibrium. But this may be a point of non-equilibrium because it is not Boltzmann. And this may happen, say, in nanoseconds, because in nanoseconds, at least at room temperature, the phonon system will equilibrate. We may describe it by temperature. And we think that what is happening this 1 nanosecond, this is actually the system, phonon system is coming with equilibrium with right. This strain, so this kind of metastability. Did I answer your question?
Yes, it's very well corresponds with optical measurements on the residual bleaching after ultrafast excitation. Yes. It's nanosecond power. Yes. Okay, Keith, you have more questions or no? You raise the hand.
I'll be brief, but you mentioned that you had access to 2D ferroelectric materials, and these could be very interesting candidates for the combination of strain and terahertz fields. Because
yes.
It's possible that it might be possible to really quite delicately guide such a material into the structure of an induced phase. So we can talk about the possibility. It could turn out to be quite interesting.
We are all thinking about the same same things. I think that there is an expert here in the participants, Wenjing Yang, who is actually doing these materials and who is studying it by different techniques. And I'm happy that she's with us. And yes, we discussed a lot of this possibility. It's a very interesting topic. And again, I say it's time and people who are involved in this.
Yeah.
Thank you very much. So let me adjourn this talk. Great talk. Thank you very much.